compute. Hi, everyone. It's a great honor for me to resume this MLC's seminar. And today we are very fortunate to invite Xiaozhe, a PhD student at System Group at ETH Zurich, working on ML system. He will introduce us with the DeltaZip work on their most recent work on multi-tenant LLMs serving. Xiaozhe is broadly interested in the area of machine learning and system, including system optimization for machine learning and data-centric systems. For more details, please check out his website. And Xiaozhe, you have the floor now.
Thank you. Thanks for having me again. And I'm very honored to present our most recent work, DeltaZip, about multi-tenant language model serving by delta compression. So needless to say, those language models have been viral in the past year. And we realize that those models are really powerful as in-context learner. So those models are trained in a very simple paradigm called next word prediction. So basically predict what the next word is. But once deployed, we realize that this model has this sort of ability to understand the user's prompt, or so-called the context. And as a developer, you don't have to like curate or even training a machine learning pipeline to handle the user's response, but just fit into a machine learning model, and the model will give you some response. So this kind of exciting ability has sparked many different type of applications, from chatbot, copilot, code understanding, translation, customer support, etc. However, I would argue that this sort of ability is not only expensive to train, but also expensive to serve. So as an example, I'm asking ChatGPT, a customized version of ChatGPT, how does indexing work in databases? And the model response is a pretty clear answer. However, if we look at the entire dialogue happening between the model and the user, actually the input is pretty long, way longer than the input prompt, the user's actual prompt. So this context is to calibrate the model's response style, train the behavior, or fit in some factual external knowledge. However, because this sort of context, the cloud providers will charge you more for the input tokens repeatedly for every request. Accumulatively, if you have a growing user base, this becomes more and more expensive as the user base grows. So even though these are very exciting for developing new apps, but once you deploy it to a production environment, it becomes really, really expensive. So we would argue that fine-tuned models are critical and will become more and more critical in the following. So for someone who is not working with machine learning, fine-tuning is basically tuning the model's behavior once you have a certain downstream task. And for many downstream tasks, a specialized smaller model may work just as well, if not better. So, and those specialized models, even though might be way smaller, like few billion parameters, would outperform 100 billion parameter models. And for many downstream applications, for example, chat, for example, code assistant, they all require fine-tuning. So as you may know, those ChatGPT is fine-tuned from GPT-3, and Copilot from GitHub is also a fine-tuned version of GPT. And with those fine-tuned models, there's no need for long context and a few short examples. So in the production environment, those fine-tuned models could actually save you money. However, as of today, those fine-tuned models are less efficient to run and serve on the cloud providers, because as a cloud provider, I can either swap those models in and out on demand. So once a request comes, I can swap them into the GPU, and once the requests go, I can swap them out. Or I can over-reserve enough resources to serve all those models, but some models may not be that hot and may not be called. And because of this smaller user base, cloud providers will generally charge you more to compensate the cost of serving those models. For example, OpenAI charges you 2 times more for fine-tuned, customized version of GPT. So even though this fine-tuned models is critical as of today, many people are asking on Twitter for a cost-effective serverless solution for fine-tuned open models. that has minimal code boot time, latency, and you pay by token. But at least to our best knowledge, as of today, there's no such a solution that provides a serverless deployment of fine-tuned machine learning language models. The main bottleneck for serving those fine-tuned models is about the loading cost. Imagine you have to load 100 gigs from NVMe to your memory, to your GPU. It's a disaster for a latency-sensitive application, right? However, it is still under research. For many papers, they simply assume that all models are placed on the GPUs and avoid the loading cost. And in order to reduce those loading costs, compression is a promising idea, but to our knowledge, as of like several months ago, the compression still fails below 4 bits. So if you compress a model to 4 bits, it probably works. But if you compress it even more aggressively or jointly compress with quantization and sparsity, the model quality drops significantly. And on the other hand, many researchers are working on new paradigm of training called the low-rank adaptation. So there are many, many new works working on serving those low-rank adapters, but all these new techniques require a completely new training paradigm. And to our knowledge, this low-rank adaptation still sometimes cannot match the performance of full parameter fine-tuning. Therefore, in this research, we ask us the most challenging question, how to serve multiple full parameter fine-tuned models efficiently, concurrently, and in a serverless manner. So there are some key insights that we can leverage. First is that many fine-tuned models stem from the same base model. Actually, personally, I believe that eventually people might converge to the same very well pre-trained base model. So in the past, most companies in the world fine-tune their own variants from Llama, and right now people are using Mistral. Eventually, once we have some open source, very good base model, people might just fine-tune their models on top of very few base models. This is also because fine-tuning takes much less training data, time, and resources. So for pre-training, you might need millions of dollars, but for fine-tuning, you can even do on your personal computer or something. And since fine-tuning takes so less resources, intuitively, the new information introduced in this fine-tuning process shouldn't be that much. And in other words, the delta between the base model and the fine-tuned model should be much smaller than it is today. Today, if you take the difference between the base model and the fine-tuned model, it takes the same amount of parameter and therefore the same size. But I believe it shouldn't be the case. It should be much, much smaller than it is today. But this is all about intuition. So we try to look a little bit deeper, and we plot the distribution of the weights in the base model and the fine-tuned model to understand what is happening in the fine-tuning process. So in the left figure is about the weight distribution in the base model and the fine-tuned model. As you can see here, the distribution fluctuates in the base model and in the fine-tuned models pretty significantly. However, the outliers almost happen at the same index. And therefore, if you take the difference, if you take the delta, on the right, we plot the distribution on the same scale. And as you can see here, the distribution is way smoother. And it's all around 0. It introduces a very high sparsity. And we observe the same pattern on all linear modules in the model. So this is extracted from a Llama 7B and its fine-tuned variants. But we observed the same pattern in almost all fine-tuned models that we have experimented with. And we argue that on the left, the base model and the fine-tuned model itself might be pretty hard to compress. But on the right, if you have way less outliers, you have a much smoother distribution, that should be much easier to compress. So what do we mean by easier to compress? Looking at the quantization from the quantization angle, so quantization is basically, originally you have 16 bits and you represent your weights in the 16-bit range. And the quantization is about, like, for example, using 2 bits to represent the entire range. So you will keep the minimum and the maximum to preserve those outliers because those outliers are usually more critical to the model's performance. So if you have some outliers, that means your quantization grid will be stretched, right? It will take more bits to represent the 16-bit range if you have some larger range. However, if you don't have that many outliers, so for example, if your distribution looks like this, that means you can compact your quantization grid. So you can use the difference between the quantized weights and the original weights in 16 bits becomes smaller. So it introduces smaller errors. So in summary, so if there are outliers, if there is a large range, that means usually you have larger errors. But since deltas are way smoother, that means those deltas are more compressible from the quantization perspective. So inspired by this observation and those insights, we built the first prototype system that serves compressed model deltas. So the system starts with post-training compression. With a given fine-tuned model and its corresponding base model, we compress the delta in 2 steps. The lossy compression with quantization and the sparsity, and then lossless compression to leverage the potentially high sparsity in the lossy compression. And then the compressed deltas are saved in the persisted storage, let's say NFS or hard drive, or etc. And we then have the serving stage. Let's say we have an accelerator connected with the storage by low bandwidth interconnection. This is where your loading cost happening. And we partition the accelerator into 2 parts, one for the base model and one for the deltas. And the base model is tapped during the entire serving stage in the accelerator. And when a request comes, we load the small compressed delta from the storage, perform decompress within the accelerator, such that we leverage our observation and significantly reduce the data loaded over this slow interconnects. And after that, we can perform the actual inference, which basically performs 2 parts of inference and aggregated the results back. So in this process, there are 2 main points. One is about how we take the delta and how we compress it and how we get the results. So I will describe them in more detail one by one. So the first question that I come across is about how to take the delta and compress. While this may seem pretty straightforward, there's already a lot of compression framework. And what we take is a pretty old but standard and effective framework called optimal brain compression. So this is a framework built on top of very old paper from last century, the optimal brain damage and the optimal brain surgeon. They are all from last century, pretty old paper. But essentially, the idea is that you can quantize and prone the weight matrix to minimize the error on the calibration dataset. So if you have a linear module, you have a dense layer, and you have the input matrix as a calibration dataset, and you can basically minimize the error happening after you take the matrix multiplication. And with this framework, those deltas can be injected really, really easy. It's like primary school math. So what you do is basically at this stage, you have the weight becomes the sum of the base weight and the delta. And you do some primary school math, and then you can find that basically you can put delta into the entire theory of optimal brain surgeon and compression, and you get something similar. Well, this may seem straightforward. So the very straightforward approach to do is that you take the difference, right? You enumerate across all those parameters, take the difference and compress it with some black box compression algorithm. Unfortunately, this doesn't work in general. So so you remember that we have those smaller scale of delta, and also we have those long linear activation functions across this forward path. So if you have a multi-layer fully connected neural networks, and you feed in the input, and at each layer, these deltas are probably like 10 times smaller, and this gets small. The output gets smaller and smaller and smaller. And at some point, the output becomes all zeros. And at this stage, your compression algorithm will complain Why you need a weight matrix if all inputs are 0? I would just set it as 0, and you have perfect compression ratio, but the compression doesn't really make any sense. So this doesn't work, unfortunately. Luckily, it's pretty easy to fix. So what we did is basically reconstruct the weight on the fly. So if you have a linear module, you not only take the delta, but you also take the weight matrix from the base model, and you can reconstruct what the actual input should look like into this linear layer. And with this linear layer, you compress the delta only, but discard the base weight, and perform lossless compression and save it on storage. And then to the next layer, you give the compressed version to the next layer, but the next layer also takes the base weight and repeat this process again and again until you get the all deltas compressed. So basically, you have to consider the base weight for every linear module, for every module that you want to compress. And the second part is about how we can serve such a model. Well, the most straightforward way to do is that we can add that back. We can add the delta back to the base model and serve a request. So with this approach, there are basically a few steps. First, you need to load the delta. We are happy here because we are loading less bytes. And then you need to unpack this delta back to 16 bits, right, in order to add it back to the original base weight. And then you need to, add it back actually, and then perform inference. Well, we are happy here because we do not introduce any more overhead in serving the inference process. And then you need to remove it from the base in order to serve the next query, which may not be hitting the same delta. So as you can see, in this process, there is a large overhead in unpacking the low precision delta. And this is not very friendly for your GPU. And also this limits batching opportunity because you can imagine this as a log to your base model. You can only handle a few requests for the very few the same delta at the same time, but you can't really serve multiple different deltas because you can't add them at the same time, right? It's a log. And this requires excessive memory usage because you unpack it and you save it on your GPU VRAM, and at some point it requires excessive memory usage. And we want to avoid this expensive process. So a quick recall is that token generation is basically two steps. One is the prefill, which is usually compute bound because you have all those input tokens known, and you can batch process them. And the other part is about token generation. And each time you generate one new token, and this is usually memory bounded because this is matrix multiplied by a vector usually. So this becomes memory bounded. And even though this is probably not a good thing, but we want to exploit this nature to serve more deltas in parallel. So what we did is actually not a very complicated algorithm, but simply don't add it back. So we can do them separately. So since all those fine-tuned models share the same base, we can perform a large batch matrix multiplication on the base model part. And for the delta part, we can perform a low precision matrix multiplication. Well, this is ideally supported by your GPU natively, but even though this is not supported by all GPUs for any bits precision matrix multiplication, we can still design the kernel to facilitate the needs. Well, there are many research around how to design low precision computing kernels for this case, for this use case. But essentially, the idea is that instead of adding them and then do the matrix multiplication, but we can separate them and do them in parallel. And I would quickly introduce some high-level ideas about how we can optimize the low precision matrix. In our case, we basically want to fuse the operation of unpacking and the matrix multiplication. So here, we fuse the unpacking and matrix multiplication. And the idea is that we move the low precision delta for each matrix multiplication from your GPU HBM and unpack it within your stream multiprocessor, unpack it there, and perform matrix multiplication and write the results back. So this, by previous research, usually introduce 3 to 5 times speed up. It's pretty significant. And in any case, there's no need for the 16-bit delta on your GPU HBM, which is pretty scarce. But instead, you only write the results on your HBM back. And this also enables batching for shared base model, because you imagine that if you have 5 times speed up, that means you handle 5 times delta. And for your base model, if you perform a batch size of 5 with a cost of 1, that means using a cost of 2, you are handling 5 requests for different models, right? And this applies to the entire transformer block. And here I'm illustrating with 2 requests, one for the base model and one for the fine-tuned model. And the idea is that you bifurcate before every linear module and amalgamate it after this module. And by doing this, you get the same result, but you can do all those things in parallel. And we evaluate the system. I will describe the evaluation shortly. So basically, we evaluate from 2 different angles. One is about the model performance, the quality after compression. So on the x-axis, we show the compression ratio, and on y-axis, we show the downstream accuracy on the fine-tuned task that we have. So this is the accuracy of our compression. So as you can see here, we compress the model up to 12 times, but the performance does not drop at all, actually. And if you use Spark GPT, which is the state-of-the-art algorithm at that time, basically the performance drops after 4 bits. And we evaluated on another task, and basically each knob here represents the configuration. So we have different bit weights and also sparsity. So here, for some tasks, it's easier. For some tasks, it's harder. But on all tasks that we evaluated so far, we do not really see some performance drop after compression. So in all those tasks, we basically maintain the high quality, the same quality at 6 to 8 times compression. And this is done for a 3 billion parameter model. So for smaller models, it's usually harder to compress. So this is a very challenging setting. And we are also trying to evaluate on larger models at this time. And there's no retraining required in this process. So basically, the entire compression can be done on consumer hardware without any training backpropagation stuff. And if the users are not happy with the performance, they can easily roll back to a higher compression, to a lower compression ratio, and get potentially a higher quality. This is enabled by efficient parameter search. In our experiment for 3 billion parameter model on a single 3090, a compression can be done in 5 minutes. And this applies to any type of fine-tuning, either it's SFT or RLHF or whatever type of fine-tuning this applies. And here's a quick demo of a chat model. And as you can see, even though compressed by roughly 10 times, this model still outputs coherent text, and it actually makes sense. And we have evaluated on 50 dialogues in the appendix of our paper if you're interested to look into. And we also evaluated the throughput in end-to-end setting. We simulate the model swapping with error traces, and we evaluate the throughput of different backends. And in our system, the model is quantized to 4 bits with a compression ratio of 4 times. And our system improves the throughput by 2 times for generating 200 tokens, and with a lambda 3 Poisson distributed workload. And on other settings, we see an improvement of 1.5 to 3 times. And also, in this case, we see that by increasing the batch size, by enabling the parallel computation, we mitigate the memory efficiency and indeed get a better throughput. And in summary, I hope I have conveyed the message that those deltas are heavily overparameterized and therefore highly compressible. There's a lot of space to really condense those deltas. And to our best knowledge, this is the first work for multiplex full parameter language model serving. And actually, this is not the end of the story, right? This is actually, we think, is a start. So there are a few directions that we are actively exploring. The first is careful mixed precision compression. So for now, we were doing the full precision. So basically, FP16 for the base model and different precision for the delta. But you can also compress the base model at the same time and compress the delta in a different bit width, different sparsity. And also you can search configurations automatically for every layer. Right now, we are using the same configuration, the same precision, the same sparsity per layer. But actually, different layers are not probably different in sensitivity of different configurations. So would it be cool if you have automatically search algorithms to find the optimal configuration per layer? And also right now, people are becoming more and more interested in compressing those KV cache and activation as well. And we were trying to explore what we can do here once we have not only one base model, but also multiple deltas at the same time. And naturally, for the multi-tenant model serving scenario, scheduling is hard, and many people are also working on this, I believe, when to load the model, when to evict, and some sort of things like that. And within ETH, we are particularly interested in heterogeneous and modern hardware. For example, Hopper GPU introduces native support for low precision FP8 computation, and we're also interested in how FPGA works in like any bits. We can probably compress to 1 bit and say how FPGA goes. And we can brainstorm a lot more space to explore. But that's basically the story that I have so far for today. And I hope I'm not over the time. That's basically everything from my side. And I'm happy to take any questions or anything, comments, suggestions.
Thank you so much, Xiaozhe, for your amazing presentation. The floor is open for the questions. If you have any questions, just unmute yourself and you can ask Xiaozhe. If not, I start first. Yeah, thanks for the amazing presentation once again. So according to this presentation, I'm under the impression that the delta modules, the delta weights were stored in the main memory and were loaded on demand to be decompressed, or is it? So if the delta models are small enough, would it be possible to just store them on the GPU weight on the GPU memory to save the communication, because that could be very expensive, the host to device communication.
Yeah, it's surely possible. I think it's more of a trade-off, like where to store those deltas. So if you have like thousands of deltas, even though you can compress it by 10 times, I imagine you don't want to put them into your GPU memory. Instead, you want to use those GPU memory for KV cache or activation or batch size or whatever. So it's more of, I would say it's more of a trade-off. So in our case, we actually imagine in a case where you have thousands of deltas and even the host memory cannot fit. So in that case, you also want to store them on your hard drive as well.
That makes sense.
That's my imagination.
How does this delta after compression, how much is the delta after compression compared to maybe the techniques used in LoRa? Like LoRa can use only 1 to 10% of the full parameters to change. How much does it compare to
So
that?
our compressed deltas are about 10 times smaller than the original model. So as you can see here, if you have like say compression ratio of 10, that means the delta is like 10 times smaller than the original full FP16 bits model. but it's still larger than the LoRa adapters, like 10 times larger than the Delta adapters. It depends on the rank, of course, but roughly, I would say it's 10 times larger than the LoRa adapters. Well, another interesting angle is that compression can be low rank factorization, so that you don't have to use low precision, but you can actually use smaller models to represent the large matrix. That's also another angle of compression. So it's hard to compare directively, but so far, in our case, it's 10 times larger than it's like in the middle of full parameter fine-tuned model and in the LoRa adapter.
Yeah, that's amazing. One last question, or maybe just a sleep of thought. Sleep of thought is that, so one I think the bottleneck will be, as you also mentioned, is uncompressing those delta weights, and that is must be done in a serial fashion, although it can be fused into a matmul. So some of the latest work like Punica and Aslora leverage a new a custom written CUDA kernel that can batch process those adapter weights. So would they contradict with the design of the leveraging such custom-made kernel if you fuse the decompression and the matmul into one? Or is there any way that we can shorten the serial part of uncompression so that we can make it more scalable? If you're thinking, if we can shorten this critical path, then we can definitely make it more parallelizable.
Yeah. So there are two ways of decompression, or we use unpacking to specifically pointing to the phase where you decompress from low precision to full precision. So you can either unpack them all, unpack a large matrix at once and add it to the base model, base weight, and perform inference. In this case, it will be pretty slow. But at the same time, what you can do is do a block level unpacking. So before every block of matrix multiplication, you unpack it within the accelerator. In this way, you can batch process. You can take a large bunch of blocks and unpack them in parallel within your stream processor. That's also possible. That's actually what we were doing in the kernel.
Oh, that's very nice. Then you can pipeline this, like while you're
Yeah.
compressing, and maybe you can even leverage FPGA, something like that, to help you to uncompress in the future, maybe.
Yeah, it's also a trade-off because
Yeah,
if you uncompress it with the other accelerators, that means you will need to move
more data, right?
some more bits over your PCIe or anything. So right now we try to do our best to compress within the highest level of accelerator. So in the SRAM.
Yeah.
Yeah.
Thank you so much. That's all my questions.
Thanks.
Yeah. If do you have any questions left? If not, we can just call it a day. All right. Thank you so much once again, Xiaozhe, for your amazing talk, and I hope to see the following work, following more work following up this in the future. Yeah.
Thank you so much for having me, and it's an honor.
Yeah, it's honor from our side too. And yeah, see you next time.
All right.
Yeah.
See you.
Mm,
Bye.
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 Thank you.